Yeah, good evening, everybody. I am Narayan, K.S. Narayan. I welcome you all on the behalf of IIT Alumni Center, Bengaluru for the 48th webinar. We have been conducting these webinars online since April 2020, since the start of the pandemic nearly. It's been a successful series. And in case you have missed it, you can go to the YouTube and look for the IITACB seminars. Today we have the opportunity to hear Sharada Srinivasan, professor at National Institute of Advanced Studies, NIAS in Bengaluru. Sharada comes from a truly interdisciplinary background. She's a BTech in engineering physics from IIT Bombay. She has earned her PhD from the Institute of Archaeology, University College London, on archaeometallurgy of South Indian bronzes. She's made pioneering contributions to the study of archaeology and history of art from the perspective of exploring engineering applications in these disciplines, as well as in performance studies. Sharada is very well known. She's a fellow of the Royal Asiatic Society of Great Britain and World Academy of Art and Science. She is a recipient of many awards, including the Dr. Kalpana Chawla Young Woman Scientist Award. She has been elected to the American Academy of Arts and Sciences recently, and also received the Indian National Academy of Engineering Women Engineer of the Year Award last year. She is also a Padma Shri recipient from the Government of India. Moderating this seminar is a colleague of mine, Shobna Narasimhan, professor at Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore, India. Shobna is also an IIT alumni. She got her MSc in physics and then went on to do her PhD from Harvard University. After her postdoc work in US and Germany, she came over to India, and her research interests have been around research topics around computational nanoscience. Shobna is again a very well-known physicist, champion of women's cause for and larger participation in science and physics. She's an elected member of the American Academy of Arts and Sciences, and also a fellow of Indian Academy of Science and National Academy of Sciences in India. So we really look forward to this very interesting session. Before I hand over the session, I would like to mention that I really would like the audience and the part to engage in the discussion via the Q&A box, not the chat box. So please pose your questions in the Q&A box. Shobna will be moderating this. And over to you, Sharada and Shobna.
Thank you, Narayan. It gives me great pleasure to moderate this session. I should mention that Sharada and I are old buddies. We met, I think, on our first day in IIT Bombay, both of us. We were both supposed to stay in H10, the only girls hostel at that time, but there weren't enough rooms, so we were both put in a flat that we shared with some other women for a few weeks till rooms became available. And we had a great fun time as flatmates. And ever since, we've stayed friends, we've stayed in touch, and the bonds built during those crazy times in IIT have stayed strong. So let me hand over to Sharada. I look forward to hearing from her. And just a reminder, as Narayan told you, please put your questions in the Q&A box. We'll have one break after about 20-25 minutes for a few minutes, and then we'll take the rest of the questions at the end. Go ahead, Sharada.
Thank you. Let me say that it's a great privilege to be invited by the IITB Alumni Center here in Bangalore and to share space, even if only virtually, with so many of my eminent colleagues and engaged colleagues, and Professor Narayan and Dr. Sushila and Professor Shobna, and of course as women alumni, Dr. Sushila, Professor Shobna, and I, share, I think, an extra special bond because in a way, I think it's the IIT environment that I always say that I owe my archaeological interests and the fact that I got into archaeology in a way to IIT because it really toughens us up, and after that we can take on anything. So, even if it's a sort of quite challenging professions and so on. And it should also say that it's a great privilege to have this moderated by Professor Shobna, who has also been an inspiration to many of us in the scientific disciplines, and also had a recipient of the Kalpana Chanda Award as well, which was mentioned and so on. So, so this talk will touch upon some of my journey, which pertains to some of the interdisciplinary work, and the topic is Wootz Steel or South Indian ukku, and some insights and explorations into technology transfers in antiquity. And as of course, like many great world civilizations, the Indian subcontinent has also made many great contributions in terms of science and technology in antiquity, or the beginnings of certain disciplines which have emerged into more in terms of contemporary times, in terms of modern metallurgy and modern technology and so on. And so this is a saga of this fascinating steel-making tradition, which of course is now all but died out, and pointing in the first part to just discussing what exactly this material is and the significance in terms of the modern categorization of advanced materials and so on, and then touching a bit on the archaeological and archaeometallurgical part of it, which I've been engaged in, and then the aspect of how it was a tradition of making a high-grade, high-carbon steel, which then moved to other parts of the world and also to Europe and so on. And so there is that aspect of the transfer of technology. So I'll now proceed to share my screen. So are you seeing it now? When I
Yes.
Yes, we are.
Yes, thank you. So yeah. So this, of course, in this slide you can see, since I think this aspect of women in STEM, it doesn't just relate to women in a lab setting, but I'm also always looking out for women in terms of craftswomen and metal craftswomen. And so you can see here, this is a forge which is actually being operated by these two women with the bellows here and so on. And of course, Wootz, well, since Sushila and Narayan were also kidding me a bit about the Bharatanatyam and so on, that I realized that my talk was just going to be very technical. So I did then just put in a touch of my background as a Bharatanatyam dancer as well, which has also been a great part of my interdisciplinary interest, maybe just to convey the sense of a foundry that I put in this particular slide, the fire and the topic of ukku, which is a term for steel, but it derives from the Tamil word, which is urukku, which refers to making molten, as I'll touch upon. Well, of course, the best known aspect of iron technology in the subcontinent is the celebrated Delhi Iron Pillar, which is the earliest massive surviving large iron forging anywhere in the world. And it is dated by inscription to the 4th century CE. And it's at a height of about over 7 meters. And it is attributed here to the Gupta period. You can see here a Gupta gold coin. And one of the first attempts to study the metallurgy of the Delhi Iron Pillar was made by Sir Robert Hatfield going back to 1912. And this is what we typically describe as wrought iron, which is basically iron with very low amounts of carbon. And you can see here that this has a ferritic matrix of wrought iron. And of course, there's been a lot of interest also because the Delhi iron pillar has been fairly corrosion resistant and earned the name of the rustless wonder and so on. And of course, there's an entire topic there, so I won't be delving on it too much, except to say that some of the reasons for it that have been postulated, that of course it's very high grade and pure wrought iron with very few impurities, save perhaps for a bit of traces of phosphorus, which might have contributed to the corrosion resistance. And there was also a paper that we had collaborated with late Professor Balasubramaniam of IIT Kanpur in our BOOMA proceedings, which had touched upon some of these aspects. And of course, there was a lot of mastery of the forging of wrought iron in the subcontinent. And another very spectacular example is the 12th century Konark Sun Temple, where iron beams were used as structural elements in the architecture because of course, the tensile strength of the condylite stone, which was used in the architecture of the Konark Temple, does not have very good tensile strength. And here these beams were actually used in a functional or structural sense, whereas of course in the Delhi iron pillar, it is mainly an ornamental or decorative context. But here they were actually used to reinforce the lintels and so on. And, over about 200 of these wrought iron beams were used. And you're also seeing here a view of this large iron cannon from the Bidar fort, which is of about the mid-15th century of the Bahmani period, which is one of the largest of these cannons. And this is also made by the process of forge welding pieces of wrought iron and building up the cannon and so on. In fact, the Delhi iron pillar is one of the let's say parts of our monumental heritage, which has been designated as an ASM international landmark. And in this case, there are other monuments such as the Eiffel Tower and so on, which have been designated as ASM landmarks. And it also has, it was accorded the status also through some of our studies made at NIAS and other colleagues, Dr. Baldev Raj and so on. And there was this plaque which was put there dedicated to the ancient iron smelters. Well, I won't be touching on too much about the iron smelting tradition, but this is just to point to how, in this case, what we call wrought iron or bloomery iron, it's produced by a process where the ore is reduced to metal in the solid state because iron has a very high melting point of about over 1500 degrees. And so the way that it was extracted was using these shaft furnaces. So it was a solid state reduction, really. And this was an experimental smelt that we were carrying out at the NIAS campus, which used one of these, reconstructions of shaft furnaces. And you will also see here, since this is an IIT-related seminar, our colleague, Dr. Smriti Haricharan, who is part of our group, who has now joined IIT Bombay as one of the faculty in archaeology and so on. So we've been contributing to this research in other parts of India as well in terms of encouraging interdisciplinary research in archaeology and so on. Well, coming to Wootz Steel, well, when we talk about wrought iron, it typically refers to, as I said, iron with very low amounts of carbon. But steel is typically an alloy of iron with more carbon, which contributes to the properties. It makes iron harder and properties of tensile strength and so on. And Wootz was really the first high-quality steel that was made in Antiquity, as commented by well-known archaeologist Verhoeven. And there are many of these accounts which you find going back to particularly the colonial records and the travelers and so on of that period in the 18th century and 17th century and so on. And they observed this steel being made by crucible processes, and it was known locally as ukku. And so this was a Europeanized term, which was called Wootz. And typically, this is what an ingot of Wootz steel looked like. And this is a specimen in the Science Museum. And to just give an example, the French scientist Romer in 1722 wrote that there is this cake which is supposed to be steel from India, rated most highly in Egypt. I could find no artisan in Paris who succeeded in forging a tool out of it. So you get a sense of the reputation of the steel, which couldn't be forged, by artisans in Europe and so on. And it was also very much sought after in the West Asian context and so on. And in fact, the repute of Indian iron and steel goes back to accounts even in classical antiquity and so on. And there's the accounts of Quintius Curtius, who wrote that during the campaign of Alexander in the Indus region, this is around 326 or so BCE, the defeated king is said, Porus is said to have presented 100 talents of bright iron of ferrum candidum. And of course, this is just a kind of a light-hearted sketch of this episode in history, which is quite poignant in a way. Porus presenting the talents of bright iron and ferrum candidum to Alexander. And, the mention of ferrum candidum is quite interesting because that refers to bright iron. And of course, we don't know what kind of iron that was being presented, whether it was wrought iron. But it's certainly the case that when you slice some of the ingots of Wootz steel, which might have been preserved, they do look very shiny and bright. So, one can't rule out the fact that this might have referred to some kind of high carbon steels. And we do know that there is some finds from the Beer Mound in Taxila of 1% carbon steel. But still, that is at this point just a speculation. And typically, these cakes of Wootz steel were made by carburizing wrought iron in crucibles so that you get this kind of crucible-shaped ingot. Now, why that is quite interesting is something that you have to go back to the iron-carbon phase diagram to try and understand. Of course, in medieval Europe, it was largely the lower carbon wrought iron, which was known, as I said, that has less than about 0.04% carbon. And of course, then wrought iron does get carburized slightly when you heat the iron over the forge and so on. So you get some low carbon steels. But the novelty of Wootz was that it was a steel with about 1.5 to about 2% carbon. Of course, what we describe as cast iron was used quite a lot in China. That has about 4% carbon. And cast iron, of course, is quite brittle, but it was used very widely by the Chinese. But Wootz has a composition of about 1.5% carbon. And what is quite special about this composition of steel is that it has a certain structure of perlite and cementite and so on. So when it was hammered, it would give this very spectacular kind of banding, this pattern of wavy patterns of perlite and cementite, which was described in Arabic, for instance, as the Damascus. And many of these ingots were being exported to Persia and West Asia and then forged. And the edge structure, crystalline structure of Wootz gave this very wavy pattern. And it had very excellent qualities, of course. This is, of course, a blade from the era of Tipu Sultan. And actually, in modern metallurgical terms, this composition of 1.5% carbon is what we call ultra-high carbon steel. Even it has been found that it has certain very exotic properties. It has high impact strength and so on. And so it was a very good kind of steel that was being used for swords. And we have accounts by travelers like Tavernier of the shipments of tens of thousands of ingots which went from ports such as Machilipatnam and so on, and from Golconda, which is modern Andhra Pradesh, to Persia and so on. And so this is just to show a portrait of the Nizam from Darya Daulat Bagh in Srirangapatnam. So this was the Persian blades known as the Shamshir. And we had also undertaken, of course, some of my studies in Wootz go back to my doctoral work from the Institute of Archaeology in the early 90s. But later on also, I continued with that work at NIAS, and these are some of our collaborators, Dr. Jill Jolliffe, Dr. Ranganathan, Dr. Jai Kishan, and so on. And even today in the area of Telangana and so on, there are a lot of these implements which are still used even in modern agricultural contexts. And in this case, this is a toddy tapper's knife, a humble toddy tapper's knife. But just to tell you what the structure of Wootz actually looks like, this is an SEM and EPMA analysis of this knife. It had a 1.5% carbon steel, and it typically has this structure of lamellar pearlite, which is surrounded by a cementite network. So, of course, there's no ferrite here, but this also tells you how that structure comes about in the Damascus blade of the alternating pearlite and cementite, the light and dark patterns. And of course, the pearlite here is lower carbon steel and the cementite is a higher carbon steel. And that gave certain very good properties, and I'll come to that later. But this is just to point out the archaeometallurgical debris which you find in the Telangana region of these broken crucibles. Because what was being done was that, at least in some of the processes, the wrought iron was packed with carbonaceous materials inside these highly refractory crucibles and then fired for very long firing cycles, as you see in this conjectural furnace. And so that the so as I was mentioning with wrought iron, it is a solid state cementation process, but here there is some kind of the iron was being heated to such high temperatures of at least about 1300 degrees, where it was definitely viscous, if not completely molten. And it was because it was really quite viscous and, at least progressing to the liquid state, that it could absorb a lot more carbon, and that's how you got the high carbon content. And this took some great deal of skill in terms of the long firing cycles and such like. And you can see another very eminent or rather interesting traveler in the region of South India just after the fall of Tipu Sultan around 1800 was Francis Buchanan. And these are some of the sketches of Buchanan, where he shows how these furnaces were being fired by these huge bag bellows. And this is one of the blacksmiths, Mandaloji Gangaram, from the region of Konapuram in Telangana, Konasamudram. And some of these are some of the crucible shards that he's holding up. And he was one of the last blacksmiths who had some sort of memories of the Wootz making tradition. And so although they're now doing blacksmithy, the actually primary smelting and so on of Wootz has completely died out in the Telangana region and elsewhere in India, of course. Now, coming back to this term, Wootz or urukku itself, that's also quite interesting because that is a term which you actually find going back to early Tamil texts, which typically refers to making molten. And so it is really that term urukku, which then becomes ukku, and then ukku becomes Wootz. Wootz is, of course, a very Dutch way of pronouncing something. So because the Dutch were also then quite active in the region of Golconda and so on. And of course, since I mentioned, my earlier doctoral work, of course, a lot of my major work was really on the study of the great tradition of South Indian bronzes and the Chola bronzes and their analysis and so on. And of course, these are typically made by the lost wax casting process, where you have a wax model of the icon to be cast, which is then covered by numerous layers of clay to form the mold. And then the mold is heated and the wax is expelled, and then the metal is poured into the mold and then it's finished. So that is really the lost wax casting process. But anyway, since Sushila was also kidding me about my dance background and so on, I thought I should also mention that there is this beautiful verse of Andal, who's very much a lot of Andal's poetry and all that are still celebrated in the Bharatanatyam tradition. And in the Natya Tirumori, she likens the downpour of rain from the clouds to this metaphor of the release of wax from the mold. And there's this very beautiful verse actually, which says, Ulle, which is the hearth, Ulle meligu urukki, that is, you melt the wax. And then again, the term urukku is used there. And then Vengala mutra, Varishevathu, and Maraye unakku. So it is like the pouring of the rain, this release of the wax from the mold. So it gives you this sense that actually there was this metaphoric significance also in some of these verses. So they didn't miss out on making observations about the casting processes and so on. And I also wanted to highlight again that this term urukku was already in regular usage in the early Tamil texts and so on. That connection with the description of how these steels were made. And then I was also able to do some archaeometallurgical work and find new production or the production sites which were not previously known for making wood steel. And this is a site in Tamil Nadu, Male Sirvalur. And here you can see again these broken crucible fragments, which you typically find in a site because in the crucibles are broken and the ingot is retrieved. And when you look at the cross-section of the crucibles, in this case, you see that it's a very highly vitrified and glassy matrix. And you have this globule here, which is what we call a solidified metal prill. And this typically had this structure of ultra-high carbon wood steel, 1.5% wood steel, where you see that there is the lamellar pearlite surrounded by the cementite. And in this case also, the prior austenitic structure is also retained, the hexagonal matrix as you see here. Now that's quite interesting because when you go back to that phase diagram, and you can see here that to have reached this austenitic temperature, it must have been quite a high temperature. And the globular structure clearly indicates that it had reached the molten state. So this is what we could call a molten carburization, at least approaching that, because there have been some doubts about whether this was actually easily achieved in antiquity and so on. So I think this is some evidence that suggests that they were able to achieve this kind of molten carburization to get an ultra-high carbon steel using these traditional processes. And this is again some electron probe microanalysis and so on of the globular remnants to tell you what we do as archaeometallurgists. Now, there's also been, of course, a lot of excitement about the Damascus Blades. There's been a whole lot of literature about the Damascus Blades and so on. Of course, Marco Polo also talks about the Ondanik, which is thought to have been derived from the term Hinduvani. And typically, this is a blade with a damask pattern from the Tipu's period. And you can see this has a tiger motif of Tipu Sultan. This is a Koftgari blade, which has, of course, this is the gold damascening method in the calligraphy. But this is what is the Damascus pattern that has been got by forging the wood ingot, the alternating light and dark patterns. And of course, there's a very fascinating account also of Sir Walter Scott of this fictional episode in the Crusades where Sir Richard and the Sultan Salahuddin, they reach a truce after the Crusades. And as part of that truce, so King Richard demonstrates, the superior prowess of his blade by cutting a bar of steel, whereas Sultan Salahuddin cuts a cushion with or a kerchief in some accounts with his Damascus blade. And he talks about the 10 millions of meandering lines of this blade and, this marvelous, the fineness of this blade that it could even cut such fine materials. And of course, there was also a lot of interest that emerged in the 80s because independently, some metallurgists like Oleg Sherby and so on were doing some laboratory simulation of ultra-high carbon steels. And they found that it exhibits the property of superplasticity, of high formability at high temperature. And it was patented and found to be similar to Wootz or Damascus steel. And what the superplasticity means is that these particular ultra-high carbon steels are very highly forgeable at high temperatures. And this is thought to have been due to this ferroidization of the cementite in the high carbon steels. And this was some of their studies related to the superplasticity. And there was also a team of Marion Reibold and so on who have suggested another mechanism for why these blades could be forged so extensively, because typically, actually, a high carbon steel can be quite brittle, but they say it's because it had a structure of a nanomaterial where you had nanoscale material of carbon nanotubes and which surrounded the nanowire cementite, and that's what gave this very highly malleable property. And since Professor Shobna is also, an expert on nanoscience, I think we should ask her to come in here with her comments on, or reflections and so on. Shobna?
So, Sharda, I think we'll take a short break here. Yeah. I don't think I can contribute too much about the nanostructures of Wootz Steel because it's outside my area of expertise, but there are a couple of questions if you would be willing to take them. One is sort of not quite on your topic. This is from Raman from NIT Trichy. And the question is there any institution in India having a good 3-credit course on archaeometallurgy? I'm keen to know.
Well, this is a niche discipline, and I think there are some maybe research institutions like ours and so on. But in that sense, I myself am at a loss to answer. I think, we need to have more of a critical mass of research and also support for research. Since most of us who've been doing it, it's really been very much on shoestring, budget and just about kind of managing to survive in the field. So it just tells you that we have a lot more of work to be done in terms of systematically supporting and nurturing these kind of interdisciplinary subjects in archaeometallurgical research.
So Sharda, I've been listening to your talk and it's really fascinating. I have lots of questions. Some of them I might ask you at the end. But the first question I wanted to ask you was, how did you get interested in this area? After doing a BTech in engineering physics from IIT Bombay, how did you get into archaeometallurgy? It seems like a perfect choice for you, given that you have a technical background and you also have artistic interests, but how did you even find out that there's such a discipline? What drew you to it? What drew you to archaeometallurgy in particular?
Yes, thank you, Shobna. That's a very good question, really, because it is quite, I suppose it was very, it's still quite out of the box, and at its time, I guess it was really quite unusual, really. Well, as you know, I did have these interests in Bharatanatyam, and I was trying to keep that up as much as I could, also at IIT and so on. And as a result, of course, it also been, traveling and looking at sites, heritage sites and monument sites and so on. And, of course, I think also, when my father was stationed in, he was working on the nuclear power station in Kalpakkam and so on. So we were very close to the Pallava monuments there and all that. And so because of dance, I had, of course, the interest in understanding the metallurgy of the Chola bronzes and the Nataraja and so on. And I started to feel that maybe, because also I enjoyed traveling and, this idea of appeal to me of documenting traditional crafts and so on. And was also inspired quite a lot by my late uncle, C.V. Seshadri, to try and look at the traditional crafts and other knowledge systems and so on. And I, because he had been working with these kinds of appropriate technology and so on. And then it was really quite by chance, but I really couldn't quite see how I might, try and do it. But then, IITB actually had such an amazing library. And then I came across this reference to this analysis, using spectrochemical analysis and ESR analysis of, metal artifacts and so on. And I just started thinking that maybe because, at the engineering physics degree also exposed us quite a bit to spectrochemical analysis and those kinds of things. And I thought maybe that's an area that I could get into. And then, of course, I did manage to get support. And then I was at the Institute of Archaeology, which has this a tradition of doing archaeometallurgical investigations and so on. So it was just for me that I managed to find a place where I could park all my interests together and all that. And then even I'd also, of course, because, I was quite interested. Another aspect that I did read up at that time was because I was quite exposed to the idea of the, the uranium, thorium cycles and so on, thanks to, my father's work in the nuclear area and so on. So, and the nuclear fission and so on. So I did also read this thing about using the lead isotope analysis, the study of bronzes and so on. So that became a direction that I thought could just tie in all of these interests. Anyway, a very long answer, but that's the way it is.
So there's a couple of more comments and questions in the chat box. One is just an answer to the question, the previous question. Someone, Sujit Roy, has said that IIT Bhubaneswar has a 3-credit course in archaeometallurgy. So it's offered to BTech, MTech, and PhD students. So thank you for that information. And then we have a question for you from Rutvij Kulkarni. I think this is the last question. We'll take the rest of the questions we'll take at the end of your talk. The question is it known why Wootz technology remained unknown in other parts of the old world despite its popularity?
Yeah, so just a couple of responses. Well, thank you for filling me in. As you know that I'm not really in the IIT ecosystem, but I forgot to, yes, that's right. I mean, all the IITs now are snapping at our heels and getting into these areas in a big way. So I'm sure they will take it to further heights and so on. Yeah, well, I won't say that it did actually reach various parts of the old world. Obviously, I've been trying to also concentrate on the data in India, to also be able to say that we probably pioneered it and then it went to other parts of the old world. But certainly you have, then the technology does reach Sri Lanka at some point, and also Central Asia, and Merv is another site and so on. But as I carry on now, as you'll see that some of the very early evidence we're actually getting is from southern India and so on, which is also in a way ratified by the literary accounts. As I go on further, I'll touch upon that a bit more. So now, do you want me to revert back to the presentation, Shobna?
Yeah, I think so. Thank you, Sharda.
Okay, thank you. So anyway, that was since we were asked, I mean, I was asked about, the other parts of the old world. As I was mentioning, this term ukku itself, it might derive from the term yegu, which is also described, used in Tamil Sangam literature of about the 3rd century BC to 3rd century CE to describe the spears. And there are also these poems of the poetess Avayar, which is dedicated to the chieftain Anchi. And for instance, these are some of these spears that you see from Adichanallur of about the earlier part of the 1st millennium BCE. And of course, we're doing more of these kinds of studies, which I'll point to. But there's a really lovely poem here, which is translated by A.K. Ramanujam, which, gives a great sense of the this bardic tradition where, of course, it's a translation, but she says, Anchi, man of many spears, is at battle. And as he sets fire to enemy camps, black battle smoke swirls around his young elephants like mists around the mountain peaks. And this is, of course, this very remarkable and grand old poetess Avayar, who's captured, these kinds of accounts of people and the chieftains in battle, following them around and so on. And so some of the archaeometallurgical evidence that I've actually been doing, and it's a very much ongoing studies, is also looking at finds from the archaeological context. And one of the very interesting sites, there are others in earlier ones, now we don't go into too much of archaeometallurgy here, but just this guide is interesting for other reasons as well. So as I was talking about the crucibles, very similar to the crucibles that I showed you in Melsiruvalur and so on, there was some iron cementing debris and such like found at Kodumanal, which was excavated by Dr. Rajan and then others and so on. And this is just a section of the crucible which has been, which I had undertaken to analyze by electron probe microanalysis. And this is a dot matrix map of the cross section of the crucible. And you can see here the concentration of the iron inside the matrix of the glassy crucible. So this confirms that the crucibles were being used for this ferrous metal production. And there have also been some chisels and so on which have been investigated by Sashi Sekhar and then myself as well, which here you can see again, this has this hypereutectoid steel structure, the pearlite within the cementite and so on, confirming that the use of ultra-high carbon steels was already being made at some of these megalithic sites. And of course, Kodumanal was also referred to as Kodumanam in the Sangam Tamil literature. And it was also a great site for the manufacture of quartz beads, as you can see here, and beads of other kinds and beryls and so on. And then eventually, by about the early century CE and so on, it was also a hub of the trade with the Roman world and so on. And many of these beryl beads and so on were being taken or sent across to the Mediterranean, and in the Tamil Sangam literature also you find the reference to the Yavanas. And of course, this is from Karur, which is quite close to Kodumanal, a beautiful signet ring with a Mithuna couple. Unfortunately, it's gone missing, but this is again a very fine example of the syncretism between the Roman and the Indian artistic tradition. It's a signet ring style, but it has a very Indian kind of depiction and so on. So, and why the Roman accounts are important is because they keep referring to the iron from the Ceres. And some scholars have thought that the Ceres might refer to the Chera kingdom of this domain, and Karur and so on is the capital of the Sangam Cheras and such like. Of course, there are other interpretations of the Ceres, but there's been further evidence, of course, of not only this trade with the Roman world, but also this context of the finds of Wootz from some of my other work. And this is this very well-known site of Patinam, which has been connected to Muziris. Muziris is also referred to in the Roman accounts. And there is talk of this trade in, again, gemstones and so on, going, of course, pepper and the spice trade and such like, going from the coasts of peninsular India to the Roman world. And this is, of course, the remains of a wharf which had been found at Patinam or Muziris, as it's called. And there was also at Carnelian in Intaglio, which was found of the Roman goddess Fortuna. This was the wonderful excavations done by the KCHR or Kerala Council for Historical Research with the team of Dr. Cherian and so on. And I was able to do some analysis of some iron nails, and this is found to be a typical structure of ultra-high carbon Wootz steel, very, well-made high-grade Wootz steel here with the perlite surrounded by the cementite and so on. So this could have been one of the traded items from these ports as hinted at by the Roman accounts and so on. So it's quite interesting when the archaeology and the accounts and so on start coming together. Well, then I've also put in this style, this slide, and I'll come to the aspect of the transfer of technology and so on in a while. But it's also interesting that there are other kinds of steels with a higher carbon content that you also find in other contexts, because you do have the Damascus blades. But interestingly, I'd also analyzed some of the blades which were used in the martial art tradition of Culinary Python, which is a traditional art form of the Malabar. And this is one of the Kalari masters here, Vijayan in Kozhikode, and his daughter. And of course, one of the specialities of the Kalari tradition is the use of the urumi, which is a very interesting kind of flexible sword, which is used in the Kalari repertoire. And it is coiled up like that, and then it is uncoiled, and they swish it all around, and there's this duel that is it's very balletic, but it's also it's dangerous as well. So you have to be very trained when you do it. And interestingly, the analysis showed that it was of perlitic pointed carbon steel, which is typically described as spring steel. And in fact, spring steel is what is being used in the pendulum clocks and so on in the 16th century or so in Europe. And already this kind of spring steel seems to have been in vogue as well to make these kinds of Kalari blades. And this is one of the last few blacksmiths who was doing some kind of work on these Kalari blades. So quite a lot of these traditions really are on the verge of extinction. So that's also a reason for trying and putting together what we can, the last testimonies. And since, of course, I mentioned Buchanan's accounts and, the blades of Tipu Sultan, and Buchanan also talks about the forges that were being used to make steel in the era of Tipu Sultan. And this is one of the sites which I had looked at called Gati Hosahalli, which is in the Chitradurga district. And this is a crucible steel production site. And so you can see these crucibles where they had been packed like this and so on. And of course, the microstructure showed that this again was made of Wootz steel. So this Wootz steel was being produced in some of these domains which were associated with Tipu's reign. And one of the accounts also talks about Getipura, you know, in Buchanan's accounts that of the Tipu's the sites associated with Tipu's Getipura. So this is called Gati Hozahalli. So this may have been, certainly it was in, you know, still being used in the 18th century, but it may have had an earlier history and so on. Of course, we need more systematic funding and support to actually look at the sites and unravel, you know, the antiquity and so on. But I just also wanted to mention that the process that I talked about as far as nail cerevallure was concerned is what we call the Mysore process, where the wrought iron was being carburized, it seems, to higher carbon steel. But there's another process which was also found in southern India and also more in the area of the Deccan and so on, which is what we called Cofusion, where basically the cast iron, higher carbon cast iron, is then decarburized, and this is done by melting together the cast iron along with wrought iron, which is low carbon iron. So you get a steel of an intermediate composition. And we also found evidence for that. Of course, we still haven't been able to establish the dates of some of these sites and so on. That's still an ongoing work, but certainly they're there, you know, pre-industrial period. And here you can see typically these are what the remains look like. This is the crucible fragment. And there were some of these green glassy slags and so on. And when you look at the structure of some of the metallic remnants in that, this is what we call, this is actually a structure of cast iron, 4% cast iron. It has this particular kind of matrix and so on. And also the slags are very calcium rich, and the calcium, of course, was being used. It also comes in with the lime flux, which is used in the blast furnace and so on. And so the blast furnace technology seems to have also been used to some extent to produce these kinds of cast iron, and then which was being decarburized to make Wootz steel. And coming back to why the Wootz steel tradition died out, of course, it seems that following the mutiny, the failed Sepoy mutiny of 1857, the scores of Indian armories were being destroyed by the British. And of course, this is again a light-hearted sketch, but there is an account which suggests that these Wootz blades were so hard to cut and destroy and all that, that special shearing machines had to be used to cut them and shear them down and so on. And in Buchanan's account, you also get a fine description that for instance, in Chennapatna and so on, that some of the steel-making forges were used to make strings for musical instruments. And this is a very beautiful painting in the Darya Daulat Bagh palace of Tipu Sultan in Mysore, or Srirangapatnam more accurately. And you see there's a lady with a tanpura, or a tambura, as we call it in South India, and some stringed instruments. And there's also a lady with a Western-style violin. So you can see the confluence of Eastern and Western influences at one level, although some technologies were dying out. Some other influences were also coming in, so there's certain dialoguing as well. And so this comes to the aspect of the transfer of technology, because the interest that many of the British travelers or European travelers and scientists and so on took in Wootz is in a way what led to a lot of discoveries in modern metallurgy and so on, because a lot of the Wootz ingots were taken away to Europe to study and experiment with. And for instance, a French scientist in 1821 did some 300 experiments just to understand the composition of Wootz steel, because it hadn't actually been discovered as to what gave the properties, the good qualities to steel, that it was actually the alloying of carbon. So they kept trying to alloy it with all sorts of other elements to try and replicate the qualities. But of course, in the Indian tradition, it was sort of uncovered more empirically. But here, this is much more in a more rigorous way, actually trying to identify what are the elements in the phase diagrams and so on. And it's interesting though that, and also Michael Faraday, a lot of his work on the alloy steels also stemmed from his experimenting with Wootz. Of course, he was the son of the blacksmith and so on. And that also paved the way for the Industrial Revolution, his work on the, Wootz. Of course, there was also the aspect of, the West sort of taking out patents on things which they observed in India, and then they developed them better. And for instance, Mouchet in 1825, he recognized that the Indian process basically amounted to what he called carbureted hydrogen gas, being used to convert iron to steel. And so he went about patenting this, and then it was Benjamin Huntsman and others went on to make crucible steel in industrial ways and so on. And so that, gave a huge impetus to the Industrial Revolution. So in that sense, there was a case of a transfer of technology. And then I'll just touch upon the final instance of transfer of technology here before I stop my lecture. But I will also be subjecting you to video before that. But anyway, so this is another very interesting aspect of late medieval metallurgy that we've been engaged with, which is the study of the Tipu era metal cased rockets, which were, of course, we know from the accounts that these rockets associated with Tipu were used, Tipu and Hyder were used, for instance, in the Battle of Poliur, and they caused a lot of, misery amongst the British in the Anglo-Mysore wars and so on. And somewhere near Nagara, which is near Shimoga, a whole lot of, cache of these metal-cased rockets were found. And we were able to actually try and look at some of the metal casing. And so this was studied by spark source mass spectroscopy in a collaborative project between ourselves and the Shimoga Museum, the Shivappa Nayaka Museum, and Nidhin Olikara and so on. And this was found to be made of a very, good quality mild steel, I would say. It has about 0.2% carbon or so. But how they managed to actually extrude it like this, very, very finely extrude and so on, it's still, a case for more study as to how they managed to do all of this at this fairly early period. And as I said, in 1780, these rockets were used in the Battle of Poliur, and they were attached to a long bamboo staff, and then some even had a knife attached to it and so on. And of course, then the propellant was put inside these metal casings. And this is, of course, further study to be done on this. But the significance is that after the fall of Tipu in the Battle of Seringamapatnam, some of these rockets were taken to the Royal British Arsenal, and then William Congreve set about trying to study these, and that also contributed to modern day inventions of the rockets and so on. So there's a lot more work to be done here on how various trajectories and such like, and the aerodynamics of it and so on. And our former director, late Professor Narasimha, had also been quite interested. So this is aspects that we, are keen to look at going further and so on. So I think now I'll stop sharing the screen and then try and get on to the video. Is that all right?
Yeah, please go ahead.
Yeah. So coming to this video, this is just a little clip. As I said, we lost most of the Wootz making evidence, but this was a part of a video that we were of a film that we've been commissioned to make for the Indira Gandhi National Center for Arts, and it's a clip from that. But I'm not really looking so much at the Wootz evidence here as just blacksmithy amongst this community of Kotas in the Nilgiris, so a sort of remote community. And it's quite fascinating to see how, since we're talking about the megaliths, this community of Kota blacksmiths are living right there amongst the megaliths and, trying to carry on with this very ancient tradition of blacksmithy there. So I'll try and get this video going. Yeah.
which were followed by tribal communities, which may well predate the other traditions and provide a missing link to the megalithic iron traditions. For example, the Kotas of the Nilgiris are a prominent group who practice blacksmithy, who live amidst megalithic cairns, stone circles, and menhirs. I'm standing here in front of the blacksmith village here in Kolimalai, and it's very interesting, this whole area. It seems to be one that's part of an ancient landscape which has been integrated so well into the life of this tribal settlement. You see here what seems to be a line of menhirs, or perhaps a stone menhirs going back to megalithic times, perhaps, because we know that there were a lot of cairns here in this region. And then as we move along, we see here the temples of the Kotas, temple for Ayanor and Amanor. And right behind also, quite interestingly, is a pillar which is set amidst some of these stones, the part of a cairn sort of context. And then we see some more 3 stones marking out the furthest boundary. And these do have a significance. As I was talking to some of the villagers, they were saying that although the men are allowed to lean against it, the women are not, when I was about to sit down and so on. So obviously this has some sort of very ancient significance in terms of the landscape and the natural setting and the interplay between the built environment and the setting for their activities, which goes back a very long way, as we see with the blacksmithy from their own accounts of it. Amongst the Kotas, there is an interesting differentiation of labor whereby the men are blacksmiths and the women are potters. This is Mr. Raman, who's a Korean, who's a blacksmith, traditional blacksmith, and Sri Sivakumar here is a pujari or a priest of the local temple.
இது வந்து ராட்டை. இதில் காய்ச்சி தான் நாங்கள் வந்து தட்டுற வழக்கம். இரவு மேக்ஸிமம் இது வந்து விவசாய ஏரியா, அதனால எங்கள் தொழில் வந்து அன்றைய காலகட்டத்தில் பயங்கரமாக ஓடிக்கிட்டு இருந்துச்சு. இன்றைக்கி வந்து கொஞ்சம் சுமாராக ஓடிக்கிட்டு இருக்கு. ஏன்னா தேவைகள் வெளியிலேருந்து தேவையில்லாத பொருட்கள் அதிகமானதுனால எங்கள் வந்து ஒரிஜினாலிட்டி வந்து கொஞ்சம் டம்மி ஆயிடுச்சு. இப்போ நம்ம என்ன பண்ணணும்னா இந்த தொழிலை வந்து இன்னும் நாங்கள் மேம்படுத்தணும்னு நாங்கள் ரொம்ப ஆசைப்படுறோம்.
The Kota priest is concerned about the decline of blacksmithy and wants to revive it and has himself trained in blacksmithy. Both the Telangana and Kota blacksmiths said that the women did not partake of blacksmithy because it was a very risky profession dealing with fire. The Kota blacksmiths, like the blacksmiths of Telangana, followed a barter system of exchange where they exchanged their agricultural implements with their other communities such as the Todas of the Nilgiris. These are some of the agricultural implements that the Kotas forged. In the past, the Kotas did their own smelting, bringing iron ore from the top of the hills. Tamil Nadu has also revealed significant evidence for high carbon crucible steel production, such as from megalithic Kodumanal. From the early historic site of Pattanam, evidence for high carbon wood steel production was found, which may have been traded from the Indo-Roman port of Muziris to the Roman world from the region of the Ceres, which may be linked to the Chera kingdom as per Roman accounts. Indeed, the Sangamera bardic poems of the poetess Avayar of the early historic period evoke the battles with spears by warring chieftains such as Anchi, with the spears referred to as ekku, which may be related to the word for steel ukku. The kotas may be an isolated example.
Yeah, well, just to, of course, these were all made in very shoestring budgets, so a bit amateurish and all that. But anyway, I mean, even in this time, this was now done in 2015. And even in the span of time, so many of the elderly blacksmiths and the people that you've seen in this visuals are no more. And so, it's really just the last vestiges. And that's why this documentary was also called The Fading Sounds of the Anvil and so on. I'm still hoping that we can get it out and so on. But anyway, it's been wonderful to have this audience for these kinds of niche subjects. And thank you so much for the interest. And I'm going to stop sharing, yeah? Yeah.
Thank you, Sharda. We have lots of questions. That was a really fascinating talk. I have questions. Other people have questions. The first question I'll read out is from M.K. Vasudevan. And it says, with all modern analytical instruments and advances in material technology, is it not a wonder that the mystery of the Delhi stupa, I suppose it's the Delhi iron pillar, is still not fully understood to the extent that it can be reproduced? Seems to be a lack of will of those concerned. Pardon me if this is a loose statement. I must say, I was also intrigued by that is it really still a mystery why the Delhi iron pillar has not corroded? I mean, you gave us some of your hypotheses, but is it still an open question?
One problem you have to understand is that it's difficult to get samples. That's the biggest problem with archaeological material, to study things in detail. So, in the earlier periods, like Hatfield could take out a chunk, but it's not been that easy. So for that, you really need to have the will to make you need to be able to take chunks out. Really, I'm sure you could get further with that.
How big a sample do you need to analyze? Like, is it like microscopic samples, or do you need bigger samples when you do this kind of analysis that you do?
It really depends, because technically I could even do it on a 1 millimeter by 2 millimeter cross section if I had the right kind of equipment and such like. Now, but coming back to the Delhi iron pillar, so there was some attempt at the non-destructive work as well, using ultrasound and so on. And of course, Dr. Balasubramaniam also made some progress with understanding the corrosion, mechanisms and so on. But I think, again, after that, I'm not sure that, I'm sure if I could get a specimen, I might still be interested in exploring it more, but that has been one challenge. So it depends on the particular analysis you're looking for in the sample size. Now, for instance, with the bronzes, because again, these are archaeological objects, you can't disfigure them. But the problem is that with totally non-destructive testing, there's limited things that you can do. So what I had actually done was, using a micro drilling with just about, say, 50 milligrams at the most, and then you can use ICP-MS or TIMS and a range of other kind of spectrochemical analysis techniques. But a lot of it depends on, some of these techniques are quite expensive. Sometimes, the best techniques for archaeology are not always available in India, because, they need to be calibrated as well for archaeological materials. So a lot of this research has been done in the labs abroad, for instance, the thermal ionization mass spectroscopy or the laser ablation, for looking at lead isotope work and all that's really mainly in labs abroad, which are quite expensive because you need ultra high clean environments. So there are a lot of challenges, So all of this, it's not easy, it's not trivial work. So every little bit of info that one can get out of something is it's.
But do you think the authorities in Delhi, the central government, they would like this mystery to be solved? Is there will to solve it? That's what the question was partly about, I think.
I think that is part of it's an accepted part of archaeological work to do, archaeological scientific research. And so, but the thing is also that as you progress, probably the techniques will develop to the point where they can be done even more non-destructively. So there is always a kind of a certain conservatism is there, which I think it's a justifiable part of the museum science profession, where you're concerned about tampering with an artifact unless it's actually already damaged and things like that.
Mm-hmm.
So those kinds of considerations are there, and I think that's I think
valid.
that's part of there are some international conventions in how you go about doing these studies, but then that conservatism would tend to be there because of the fact is that when an artifact gets a stable patina, in the case of a bronze, or even for instance with the iron pillar, there's a stable patina, and you take out a chunk, then you disturb that stable patina, and so you set off a corrosion mechanism as well. So that is part of the conservatism in terms of not sampling an artifact. And so there are some scientific reasons also why one wouldn't unnecessarily encourage that. So there are a lot of factors to be taken into account in all of this.
So I was very fascinated to see your photographs and videos of these blacksmiths who have preserved these ancient traditions, presumably in an unbroken line since very ancient times. And as you said, it's very heartbreaking to think that this tradition might now be lost. So there's a question about that from Rajiv Sanghvi. And he says, are you working on any strategy to redevelop this lost skill? I'm interested to be a part of this if possible.
Yeah, well, thank you for the interest. The point is that in a way, there's just so much to be done, and we're already so swamped. I feel like there's lifetimes work to be done. I've already done lifetime work, and there's enough on one's hands just publishing what one has done and so on. And, reviving it's let's say that the work that I'm doing with the archaeometallurgical work is mainly trying to understand what was done and putting it out in terms of scientific literature so that it's there. Because once you scientifically ratify that this was done in this way, that is different from the revival, because then it's there on the record that, for instance, this archaeological artifact actually has a remnant of ultra high carbon steel. So it's not just speculation or that this was actually being done. So that's the value of what I'm doing as an archaeometallurgist. The other aspect, the revival, that we've in a way, yes, it is, the whole idea of experimental archaeology also in a way is about, of course, experimental archaeology. The idea is maybe the end product might not be a revival, but the experimental approach to trying to understand how it was made, not in a modern laboratory condition, but in let's say more organic environments, or more what we call low-tech environments, is a way of understanding the steps and how it might have gone through. So that's why in a way our iron smelting, we were trying to understand how would you design that shaft furnace, how would the blowers be placed, and this and that. So that gets you to understanding the archaeological steps. But the thing of getting to the point of revival, I think it's so you have to take one step at a time. It's not just a magic wand that you can just get to that stage, and you also need to get a lot of blacksmiths together who would be interested and train them and so on. So these are challenging things. It's not as I said, as with scientific work, it takes a lot to come out with a solid piece of evidence that you can put down. It's not as simple as just saying, oh, this. You have to be quite careful and not be categorical and be kind of cautious in what you report and everything. So I think the rigor has to be maintained, and that takes time. So you can't just have a magic wand solution that tell me how it was done, revive it now, this and that. We sort of, and the support is the other problem, because it's this constant, in the sense it's not. So, you have very well recognized disciplines, like nanotechnology, this and that and all that in science. But here, this is something which neither falls into archaeology, neither falls into science, neither fish nor fowl. So, so far those categories hadn't been created. We've been sort of working on it. For instance, the DST now had a call, called Shri, which was to also look at heritage and so on. So these things are happening, but, so steps are
Okay,
there.
he has a follow-up question. Any study done on the environmental impact of this ukku technology? For example, in the processing of stainless steels, chromium poisoning can occur and is harmful. So does this have any harmful side effects?
Yeah, well, that is an interesting question, because I think the environmental thing is we're just at the stage of trying to understand how the metal was made and processed. But this is the next step. I think also is an interesting aspect in the whole study of archaeometallurgy. For instance, in the past, the forest that would have been cut down and this and that and the other. And I mean, some kind of technologies you do have. For instance, if there is, like I've watched in the Nilgiris, for instance, the extraction of gold, they use mercury and so on. So there is actually mercury getting into the environment, poisoning and so on. And these could, in fact, try and be, you could look at them as tracers also to try and track what sort of activities might have taken place. It's an interesting idea, and I think these are the kinds of questions which could make for interesting future archaeological projects, looking at the environment and how that would, impact. So I think these are important and interesting questions.
So there's a question from Sharvarish Vaidya. What's the difference between iron and ukku? So I had a somewhat related question. I mean, what exactly is Wootz steel? Is it the percentage of carbon that makes a steel a Wootz steel? So can you just explain a little bit? I mean, you talked about it, but it was not completely clear to some of us.
Yeah. Yes, absolutely. It's the carbon content that makes all the difference, because the iron has very little carbon as such, less than even 0.04% carbon. But what happens is, as you get more carbon getting into the iron, it becomes harder, and it has, but of course, most of the contemporary steels we use are not ultra high carbon steels, because, the processing of ultra high carbon steels was not easy. And so that's why, and they can be brittle. And so they had actually specialized blacksmithy in terms of forging these ultra high carbon steels. But the normal steels we have today are like mild steels, which is about 0.4% carbon. And mild steels are good for most of the normal kinds of things, like the construction and this and that and the other. That is what is mainly used today. So we don't actually use ultra high carbon steel very widely anymore. This is in that sense a bit of an obsolete material. And of course now with, if you look at the industrial revolution to what.
Yeah, so there is a related question, just let me cut in a bit, from KK Venkatesh. Are there any potential areas of application once a sophisticated version, in quotes, of Wootz steel is eventually developed?
Yeah, so I think these are the, because it is, you can describe it as an advanced material in a way. That's what, we stated in our book, because of the fact that it has this property of superplasticity, which is, the high forgeability and so on. And so what that technically could mean is that, perhaps it means, there was one, I think, idea about whether it could have been used for railroads and things like that. For instance, when the trains go over the tracks, because of the high temperatures of plasticity and so on, it can, it has that ability to maybe take kind of wear and such like. But I think perhaps these are the kinds of directions in which, more research and more funding and so on could be done. Or, I think there was also some question of using them for ball bearings and so on. But I think also to some extent, when you have so many composite materials coming up and things like that, maybe, in fact, the whole iron and steel, industry has in a way been overtaken to some extent by other kinds of composite materials and reinforced and such like, and so on, cermets and so many other things have come up that unless there's a real necessity for them to go back to older materials, that may not be seen as being necessary.
A lot of people are concerned about the dying out of this technology. You've already answered one question about whether you're going to do something to bring it back. And I'll just read out a couple more.
If some of the rich IIT alumni would like deposit like plenty of money for me to do something, I'm sure I.
Yeah, let's.
But other than that, I mean, we are very, very. I mean, I'm just struggling every now and then just to keep, you know, the sort of fires burning. So.
Yeah, so let me just read out the questions and comments about it. One's from KK Venkatesan. It says, I read somewhere that after destroying the skilled workforce, the British deployed all the artisans as coolies at seaports. Is there any attempt to identify and bring back such skilled artisans? And Maitre Deshpande asks, 1 second, let me just find the question. I lost it in a moment. Just give me a second. Are there any efforts being done to preserve traditional woods making techniques? Is the traditional method completely lost now? Or are there any castes or groups still practicing it?
Well, in India, technically, the traditional castes, I said, like you saw in Telangana and so on, the ukku Kamari and all that, they've stopped doing all this. Also because there was the Reserve Forest Act where, you know, they couldn't get the ore and so on. So a lot of the traditional smelting also died out because of all that. But, you know, you do find that, and after all, the artisanal sector is an informal sector, and many of the traditional blacksmiths have become absorbed in, you know, construction and this and that, the kind of construction jobs and things like that. So that is where a lot of them have got absorbed. And but of course, what is happening in terms of revival, mostly most of the energy is really abroad, where blacksmiths who, you know, in a sense, because I think what is also needed is that the traditional blacksmith needs to then be exposed to modern science and modern scientific understanding and all that. Then they can get engaged, re-engaged. Because that's what's happened in the West, that, like, you know, when you say blacksmiths, I mean, obviously they're educated and things like, they understand what they do. Like Verhoeven, who's a metallurgist and also trained in blacksmithy. So then he has done a lot of laboratory simulation and made boots in laboratory conditions and forged the blades, Verhoeven and Penray, and they're published in Scientific American and all that. So there's a lot of interest in that. You'll see even on the, you know, web pages and so on of many people in the West who have, you know, or you know, Japan and so on, who are working with, in a way, it's a partial laboratory reconstruction, but then also trying to use things which approximate to those materials and so on. So there's a lot of work of that sort. But I think that, you know, in the Indian circumstances, we also need to, that's why, for instance, when we did our iron smelting, we deliberately got Mangama, the lady blacksmith in that forge, you know, the marginalized women blacksmiths and things like that, to come and actually watch and see, so that there's a two-way learning. Because, you know, as far as she's concerned, she's only seen the metal coming in the metal form. She had no idea about the fact, you know, what goes into the making of it and so on. So I think that's where, you know, we can have a more participatory aspect, you know, as far as archaeology is concerned, an interface where we also try and, you know, reskill the traditional artisans and so on. So that's where I have some
sort of related suggestions, like again from KK Venkatesan. Is there any involvement of companies like Tata Steel in any such initiatives as a new area of application development? And Sharvaresh Vaidya, should the government create a wing regarding these types of rare and important research studies?
I mean, I feel that a lot of these things are sustained on personal interest and so on. And I, you know, feel that the thing is exposing people to the possibilities.
But do you think more is needed?
Well, I mean, I don't want to keep advocating, because yes, of course, more support will always be good. In fact, our book was supported by Tata Steel and so on. But I feel that it really has to be a research initiative, and I don't feel that we should get too much of, sometimes research gets killed when too much of formalization happens, right? Because it goes into other directions and such like, yeah. So I think it should stay in the research institutions domains.
We have time just for maybe 2-3 more questions. One is from an anonymous attendee. Who asks, regarding the Delhi Iron Pillar, do you think that there is more to it than just the composition of having high phosphorus?
Yeah, there is definitely. I think I probably have to save something for a paper, you guys. I can't be answering everything. I mean, that's not fair because I find that I'm like totally like, what do you call it, up for grabs in this webinar era because, you know, everybody wants webinars in traditional science. So I, you know, like, I have to like put it all out there. Yeah, well, you know, of course, it's also been talked about that it's the relative humidity and so on. That is one thing, of course. And of course, this formation of this passive, you know, this passive compound and so on is one thing. But then also, you know, the slag distribution. So there are various factors to it. I'm sure it's not, you know, there would be, it would be a lot of other kind of factors. And the other thing is it's not totally corrosion resistant either. If you go and see now, I mean, it is developing. There are some parts which I see some corrosion coming in with the environment. So there's, you know, not much to be done there. But I think I'd like to save some things for a paper if you don't mind.
There's a comment and question from TV Vijaypala, who's logged in from Sri Lanka.
Oh,
This
nice.
interesting and wonderful presentation. Thank you very much, Professor Sharada Srinivasan. I have one question. Does the organization you work for organize any short courses or field sessions for scholars around the world?
So, you know, ours is actually a very small organization and a small research group. So, but of course, I do see now that IITs and things like that are getting active. But so we, as I said, it's all a question of, I mean, the will is there with the resources and things like that. But certainly, you know, we try and do our best under the circumstances. But
there's clearly a lot of interest. So do you think we could start some initiative to increase the community of archaeometallurgists in India or in Southern Asia, South Asia?
Yeah, I think that, you know, is definitely, you know, something which energy has to be, you know, put in that direction. At the moment, of course, speaking for myself, I just have my hands so full with things to do. I almost feel like, no, I can't take on anymore. So yeah, there's a next generation that has to get in there and fill these gaps and things like that. I mean, we've all tried to do our best, and sort of it's time to pass on the baton for someone else to, you know, take up those challenges.
So I have a couple of questions for you. One is, you talked about the Wootz Steel being shipped to Damascus for making the swords. Was that always done, or after some time did they start making their own steel in Damascus? And the other question, sort of related, I have is, you talked about, your title had the term technology transfer in it. So was the technology transfer just in one direction or in multiple directions? And do you think this technology is indigenous to India, or did we get it from somewhere else? Is anything known? I realize these are difficult questions to pin down and answer.
Yeah, and these are all, I think, questions also for future work to get more clarity. Well, certainly, I think what I have tried to, or rather what my research does point to, is that some of the very early evidence is clearly coming from southern India. So, you know, but I don't want to be too categorical because tomorrow, and I think it's, in a way, I'm not so much hung up on saying we did this first, we did that first, and rather that we just look at a particular site and find out what was going on. And then, yeah, slowly these pieces come together, but I'm not fanatical about all this. But it looks to be that is, you know, something that we can say, that it seems to have been, you know, origin seems to be.
And, you know, you've talked about how they put in some carbon into the steel, and they either had nanopressed it, so they had nanostructured it.
Yes.
But presumably they were not aware of what they were doing, right? It was
yeah,
just
that blade, of course, and you know,
process.
Yeah. And of course, when you give a talk like this, everything, the timelines of everything is collapsed. But actually, there are a lot of different things going on at different times and so on, because I was concentrating more on technology, which is another difficult aspect when you're giving these kinds of interdisciplinary talks. But the blade that we're talking about is 17th century, really, with the blade that was studied, and, you know, so the nanowired, the carbon nanotubes were found and so on. So at that point, you know, looking at so again, we
Still empirical, right? I mean, it was an accidental.
Absolutely. No,
Yeah.
because I mean, in fact, the thing is, the whole field of nanotechnology is also something which only because of the scanning, tunneling, microscope, and so on, we've been able to find out that there were such things as nanomaterials. So that is, quite a recent, science in a way. And then what we're doing is we're examining the archaeological artifacts and saying, oh, so this is a reason why it had this behavior, because it was a nanomaterial. It's not that they actually had any clue what they were doing, but they were. Yeah. I mean, the thing is that the one thing one can say is that the manual ability, right? The ability to hand make things to such precision and all that, it is really something that they were able to.
And in a way, it makes it more remarkable, I think, that they, without the underlying knowledge of microstructure or nanostructure, they were still able to engineer such marvelous things, I think.
Yes, absolutely. That empirically, just by trial and error and so on, and then repeating, and then in some ways finding a way to replicate something that they mastered and so on. That is quite phenomenal, really. Like now we have phase diagrams and this and that and the other. So, I think, but both sides of the story for me are remarkable. I'm not one of those who just says, oh, we did everything, so how great. But it's also remarkable that the science of it has been studied so much with what we might call modern science or Western science, where, the 300 experiments were done by Brion to understand what was going on in Wootz and, the phase diagrams that were made. So I think both stories are remarkable and, they complement each other. So I'm not going to come out of this just saying, oh, what is this? What did we do with, India had everything and the West had nothing. Let's get out of all that. Let's just look at science as science. It's not got anything to do with boundaries and so on. And let's celebrate art and science in a universal way. That's my take.
Okay, I think that's an excellent note on which to end. Thank you, Sharda, for a very fascinating talk. There were a few questions I couldn't get to, so maybe you can look in the Q&A box later just to see what people asked you. But the majority of questions we've addressed. Thank you again for a really fascinating talk, and thank you for giving me the opportunity to be a part of this event. And over to Sushila now.
Thank you very much. We've been indeed honored to have had such eminent scientists, two wonderful leading women on our panel today. Thank you so much for being part of this, Sharada and Shobna. We really appreciate it. I think at IITACB, we are very thankful to both of you for having taken this up. Today's session was a really very, very fascinating session, and all of us learned a lot in this. The next time I go to a museum and someone says, this is an old damaged sword, I'm going to recognize it as not a damaged sword, but something that was made in antiquity and something that we should all justifiably feel proud about. We started today with I think a very interesting statement that when we think of women in STEM or even about STEM in general, don't think of just formal courses, but look at where science and tech are actually applied and professions that apply these. Okay, so today we looked at ukku or Wootz Steel, and there was a statement that said this was the first high quality steel to be produced in the world. This steel was prevalent across South India. We saw visuals of locations in all the southern states where this was being manufactured, so Kerala, Tamil Nadu, Karnataka, Andhra, Telangana. So your illustrations and the visuals were really very nice. They I think, helped to really enhance our understanding of what we were really looking at when you said Wootz in antiquity. This steel was much sought after in Europe and the Mediterranean, and the famous Damascus sword used our ukku. So in a sense, India was already at the heart of global exports centuries ago, and in manufacturing, not software. So that again is very interesting to know that. So what exactly is this Wootz? High carbon steel, 1.5 to 2% carbon typically, And with this content and the sort of process of manufacturing that is used to produce the steel is what gives this steel several very interesting properties. And superplasticity, nanostructures were two of the ideas that you mentioned. Then it has alternate wavy patterns of pearlite, cementite, and so on. And it was used, the steel was used in many different ways. So we looked at its being used in swords. We looked at its use with spring steel, so the urmi of Culinary Python. Then its use in musical instruments as strings. So a lot of different applications of this whole the steel, and obviously many different properties that made it useful in these different applications. We saw two processes today: the carburizing process, where the furnace fired for a long time at 1300 degrees centigrade, resulting in a viscous process which allowed it to absorb more carbon. And that's, again, the reason why you have high carbon steel. And Cofusion. He also talked a bit about the crucible. So, we saw an overall picture of this whole Wootz Steel manufacture today. It was not just about, just the science it's everything. It's a holistic picture. So how do we know about antiquity? You quoted from Nachiyar Tirumuri. Interestingly, it was just last week that I heard someone describe this very same poem. So it's very interesting to see it come up in this context. The Sangamira literature, and also evidence from other parts of the world who have been recipients of the steel and have used it for various applications. And then finally, the transfer of technology, how Michael Faraday worked on alloy steels, which resulted in the transforming the whole industrial revolution and where we are today. Precursor to modern rocket technology, and how Tipu caused angst to the British, how William Congreve then took it back and was influenced by all of this. So, we ended with a very fascinating video. For me, Kotas is always related to coffee as a Bangalorean, right? I would have never, ever related it to ukku or Wootz Steel, something that has had such huge international impact. And I don't know whether the tribes there really are aware of the tradition that they are carrying. Finally, I just want to say, so again, thank you very much. Totally fascinating and a very, very informative talk today. I just want to conclude by saying at IITACB, we'd be happy to debate and work with you to facilitate some kind of initiative to revive this traditional knowledge systems around this and the processes but what we'd like to do is really bring together industry, interested individuals, and the IIT system, and of course yourself. You cannot escape, such an initiative. But we'd be happy to debate and discuss how we could possibly do something like this. Maybe put together a project that actually makes some of this happen, because it is significant, it is important, and it is something that we must get into deeper. That's my takeaway today. So once again, and thank you so much to our audience, because you come up with some wonderful questions, and it really made the whole discussion as well as the webinar so interesting. So, and please do look at our IITACB YouTube channel. Monday, we should have this webinar up there. So thank you once again to everybody. Shobna, Sharda, thank you so very much for this webinar. Goodbye.